We do. Okay, it's about 7, so in order to keep things timely, why don't we get started? I just want to quickly introduce our presenter for the day, Dr. Carl Skinner. He's coming out of the U.S. Forest Service Pacific Southwest Research Lab. He's got many decades of experience in fire management and fire management research. So without further ado, I'm going to hand it over to him.
Thank you. Well, I always appreciate being asked to come back to Mount Shasta because, I lived here for 10 years and really enjoyed it, and I love coming back. And worked here for the Forest Service for that period of time in fire management. And left the Forest Service in fire management here to go do fire research. So that's mostly what I'm going to be talking to you about is this idea of how fire shaped forests in the past and landscapes, and then how things work now, because we've changed things tremendously. So, are you going to be the advancer?
So.
One thing that we know is going, I should put a new graph up here. This is the area burned in the 11 western states, and over the course of the time since official fire suppression began. And these actually, here in this part, are a little short of where they should be. They should be coming up somewhere up into here instead of as low as they are, but that's what the records are. The records aren't really good when you go back before 1940. But what we see when you look at this is some interesting trends over time. And you see that there was a lot of fire at the beginning, and then it drops. And we got a really good drop here in the 1930s. And what do you think that was?
Logging stopped. There was a logging boom from 1880 to 1925.
But something else happened in the 1930s.
Well, depression.
The depression. And
Gasoline engines.
and the CCCs. Yeah. And they had camps, and they put them all out there in the woods, and they had to have something for them to do, and so they started putting out fires. And it's one of the things that they did. And so there was a big drop there. And then what we get is another big drop that happens after World War II. And after World War II, one of the things that helped us is at the end of the war, there's all kinds of equipment that is now surplus. Airplanes, cats, trucks, stuff that was given to the agencies to do stuff with. And so we got really good at putting out fires for a while. And the thing of it is though that everything kept growing. The fuels are still accumulating, even though we're doing a really good job of putting out fires. And something happened here. In the 1970s, we see an upturn taking place in how much area is burning, and it's continued to go up, even beyond what I showed here. And part of that, we think there's two reasons for this. Number one, the fuels caught up to us. And number two, hey, Brad. And number two is climate change. The climate's been warming. Fire seasons are getting longer and such. And so we're getting a lot more area burned. And this year is just an example of that, how early fire season started in a lot of the interior part of the Southwest and the Rockies. So, history of fire. Our general view of fire is one like this, because this is what most of the public really sees on TV. And this is the fountain fire in Shasta County, and this is the kind of stuff we would like to avoid. It's an interesting one because this burned within a mile of where I grew up. I grew up on Hatchet Mountain, and that area, and it burned 45,000 acres in one afternoon. Next. But total of 60,000 acres just in 3 days. And next. And over 300 homes. But there is another aspect to fire that we don't often get introduced to these days, and that's what I've been studying. So next. This is what John Muir said about fires well over 100 years ago. It says, in the main forest belt in California, fires seldom or never sweep from tree to tree in broad, all-enveloping sheets. Here, fires creep from tree to tree, nibbling their way on the needle-strewn ground. Of course, that wasn't everywhere, but that was a typical kind of thing in a lot of forested areas. Next. And even after, so this is in the 1930s over near McLeod, you can still see the general structure of the forest, what they were like before when fires were coming through fairly frequently. You know, high crowns and not a lot of ladder fuels and stuff underneath. Now the shrubs have had a chance to grow a bit in there since this was the 1930s. Next. Now not all fires were low intensity. I don't mean to imply that. And here's, actually here's Rainbow Ridge right there. This is Mount Eddy. And these are brush fields. This was in the 1930s, taken by Wieslander when they were starting the soil vegetation surveys of California. And so there are places, especially places like this, where you get kind of a wind corridor through this area here that we're in, and it can create some pretty intense fires under the right conditions. Next. And another thing, a giveaway for intense fires is knobcone pine, which you get on the ridge up here between here and McLeod, and you also get it over around Lake Siskiyou. And that's a tree that's like lodgepole in the Rockies that it hangs onto its cones until it burns in a crown fire, and then it releases the cones. And then it comes back with the next generation and grows densely and wants a severe fire. That's the way, and so when you see that species of trees, you know that severe fires are not uncommon in that area, even historically. Next. And then here's also Rainbow Ridge, and you can see that there are trees on the top, but there's a lot of brushy areas, and this is like 1933 and stuff. So there's, you know, some places burn pretty intense, some places didn't, but forests in general, if they were areas that were forested, have a tendency to not burn so intensely, otherwise you wouldn't have those big old 500-year-old trees. So next. So this is what C. Hart Marion said. He actually said this here in Mount Shasta. After doing the survey of the Mount Shasta area, he was the chief of the Division of Biological Survey. This was when they were getting ready to set up the National Forest System. They surveyed the mountains and forests of the West. And he said of the hundreds of persons who visit the Pacific Slope, California, every summer to see the mountains, few see more than the immediate foreground and a haze of smoke, which even the strongest glass is unable to penetrate. And in fact, most of the summer, he complained about how they really couldn't see much around here other than their plots that they were actually working on because of how much fire was going on. Next. And this is what John Liebert said. He was the lead forester for the Northern Sierra and the Southern Cascade area. And he said the most potent factor in shaping the forests of the region has been and still is fire. The general character of the forest, in fact, almost every phase of its condition has been determined by fire. That's what he wrote in 1902. So, what's going on? And how things are very different. Well, this is what we have here. This is the Mediterranean climate. And this part of California and into southwestern Oregon has this particular kind of climate. And next, it's characterized by cold, wet winters that grow lots of stuff, fuel, and warm, dry summers. We have an annual fire season. That's different than almost anywhere else you go in the country. Most places, if they have a fire season, they have a drought. We have an annual drought, and we plan for it. That's what we have. And so that's why fires here in the past were such a prevalent part of the system. And regardless of what people are doing, we have thunderstorms. So no matter how good you are at preventing people from starting fires, you're still going to have fires. Next. This is where this kind of climate is found in the world. It's actually fairly rare. And that's why you get so many people crowding into it, usually where it's found, because it's a pleasant kind of a place to live. And you can see it's just a sliver of Western North America. But one of the things that's interesting about it, even though it's that small, next, That's where 30% of the U.S. National Wildland Fire Management money is spent because of the annual fire season and so much tendency to burn in this area. Next. So I'm going to compare it to other places by precipitation patterns to show you how unusual it is. And the first one here, next, is in Nebraska. It's typical central continental climate. If you go from January month by month to December, what you see in terms of when the rainfall comes, when precipitation comes, it comes in the warm season of the year. The cold season of the year is the dry part of the year. And that's very typical of central continents and such. So basically, in order for you to burn there, you got to have a drought. Next. This is Yellowstone. You can't tell what time of the year it is by looking at how much precipitation you get. It changes form from month to month, but basically, unless you have a drought, you're not going to have much fire in a place like Yellowstone. And that's typical of much of the eastern United States as well, is that kind of pattern. Then we have Flagstaff. Now Flagstaff is an interesting one because you have wet winters because it's close enough to the Pacific to get the frontal systems coming through, and they haven't totally dried out yet. And so you get this winter wet. And then you get spring, though, is your typical fire season. Usually late April through June, and then in comes the monsoons. The heat sucks in the moisture from the Gulf, and they get summer thunderstorms that shut down fire season, unless they're having an unusual situation. And the monsoons are already starting to move into Arizona and New Mexico. They haven't made it to Colorado yet, as the news is letting us know, but they are already moving into Arizona and New Mexico and calming down the fires that were there. And because you could really see widespread thunderstorms in the last week or so in those areas.
Carl, I can't read the vertical scale. What is it?
As intended, because it doesn't matter. It's because I didn't want you to get lost in the numbers.
Because if that's inches, then no way does
No,
Flagstaff.
it's centimeters.
Okay. Well, even still, that's a lot of rain per month for Flagstaff.
Yeah, well, yeah, but the main thing is the pattern, is what gives us our fire seasons and stuff. Now here's Redding. The dry season of the year is the warm season of the year. And so that's why we're set up to burn. And when it's the cool season of the year is when we get our moisture. And so it's very different than most other places. And then here's Mount Shasta next. There you go, just like Redding, except a little cooler. And I put the temperature in there for Mount Shasta. You can see it's the same kind of pattern. And so this is what's called a Mediterranean climate because the biggest area of the earth where you find this climate is around the Mediterranean. Italy, Spain, Greece, places like that, and such. And so we're set up to burn because of this.
Carl, is anything changing in regard to climate change? What's this doing with climate change? Is any of it things?
Fire season is getting longer, is the main thing that's happening.
You're talking here in locally.
Yes.
Is there any change in Yellowstone and Nebraska?
West-wide, fire season is getting longer.
Oh. That figures.
And actually, I have a slide for that later. Next. We also get this, and so next. You've heard the old adage that only you can prevent forest fires, and CDF's always telling us that humans are the ones that cause fires. Well, the red dots are where you get the dominant fire starts are from lightning, and the blue dots is where it's humans. So of course, where you have a lot of humans, you got a lot of blue dots, but when you get up into the mountains, it turns red because lightning becomes the dominant source of fire. And such. And so you can see that especially here in Northern California, that it doesn't matter what people are doing, you're going to have plenty of fire anyway. And some years you have moisture with the thunderstorms and some years you don't. And that really determines how that year actually goes. Next. Now, one of the things that I do is I study fire scar tree rings and try to reconstruct what has happened in the past and from stuff. And so when you're wandering through forests, you can see these old scars at the base of trees. And in fact, most of these trees aren't there anymore. This was taken in the 1930s. But you can still find places like that. And those are fire scars. And people will look at them and next. And you see something, this is what they look at when you come up close to it. And so you look at this and you say, oh wow, there must have been a fire here sometime in the past. But actually, if you know what you're looking at, there's a whole lot of information there because there's more than one fire. There's many fires. Next. Every one of those folds is a separate fire that happened as that tree was growing. So this particular tree survived 33 fires over its life period. At least. Probably more, but that's all I can tell you from the outside. And so what we do next is we find stumps, and we cut the stumps, and next. And then we look at the patterning in the rings. And so like in this one, this tree is growing from this end to here. Here's the outside bark. And so when the tree was this big, each of these rings is a year's growth. So when the tree was this big, a fire came along, that was 1729, and scarred that tree, just like if you got a scar from a burn. And then what the tree does is try to heal over. That's what those creases are in the trees that you see, is where the trees are trying to heal over and cover that scar. Some trees do it a whole lot better than others. Pines don't do it very well. And that's why they're really good recorders of scars, because they leave these open areas with pitch and stuff that can scar the next time a fire comes through. Douglas fir, wham, they close them in. And so oftentimes people have the idea that Douglas fir forests don't burn much because they don't have a lot of these scars showing in them. But they actually cover them over and heal them up very rapidly. And so anyway, and then as it's healing, another fire comes. And so it begins the process again, and then another fire, and then another one, and so forth. And so that's what we look for as this kind of record, and we put together a bunch of them. And something else we can do next is actually look at the individual rings and look at where in the ring the fire occurred. And that tells us the season, the timing in the year when the fire occurred. Because the rings, say this tree's growing in this direction, and this is one ring, the light colored wood is the fast growing wood in the spring. And then as the tree starts to shut down and run out of moisture and stuff for the year, it puts on darker and darker wood until it stops for the year. And then it becomes dormant and waits for next spring to start growing again. And so we can look at that process. And so if you look at this ring right here, you see that the fire was late in the year. It was right at the boundary of the rings. And so that tells us it was probably August or early September fire. Look at this one. It's in the early part of the growth of the ring. Here's the ring over here, and you can see that where the scar was when it had only grown just a little bit that year. So that was a very dry year where the fires actually started in the earlier, probably late May, early June, that particular year. So we can see the timing and see how the fires moved around in the landscapes if we can collect enough samples over time. And then what we do next, and I won't give you too many of these kind of things, but that's hard. This comes from our Blacks Mountain Experimental Forest, which is a 10,000 acre forest just north of Lassen Park. And we've collected hundreds of samples over the 10,000 acre area. And each of these horizontal lines is a plot that's about 150 acres in size. And each of these white bars that cross the line is a fire that was dated on more than one tree in that plot. So, and you can see how often those fires were dated. These are the years down here. And, but then what we can do is look over the entire 10,000 acres and look at how big were those fires. And not only were the fires coming fast, I mean very frequently, you can see down here, this is multiple fires on multiple trees on multiple plots. And they're coming very frequently up until we started putting them out. And, and they were not only frequent, but they were big. And that's one thing that a lot of people don't understand is how much area they actually would burn. Just because they were frequent doesn't mean they were little. And because of doing this, we've done hundreds of these studies from northern Mexico to southwest Oregon. Next. That's how much, whoops, that's how much acreage is estimated to have probably burned in California in an average year before we started fire suppression. Yes, sir.
So they're frequent and they're big, but they're obviously not stand replacing.
Yeah, or we wouldn't have those trees to tell us about them.
Correct.
They were mostly low
Low
intensity
intensity.
in the general forest areas and stuff. Otherwise, these trees wouldn't be there to tell us about them. And the oldest tree we measured, and the oldest fire scar we measured here in Northern California was in Douglas Fir, over by Hay Fork. And the oldest fire scar was in the 1100s in that particular area, and that tree scarred many times, and others around it over its lifetime. That's the oldest one we found. We found quite a number of them actually that are that old, and with lots of fire scars in them. But, go back. But this 4.5 to 12 million acres a year in California was what we estimate probably burned before we started fire suppression. 2008 is the biggest year on record for California since fire suppression began, and it was only a little over 1 million acres that year. So we're kind of behind. If you think of it that way. Okay, next. And this is what a lot of the forests would look like. And this isn't even a historical picture. This is a contemporary forest. It's actually on the Lassen National Forest in the Issue Wilderness area, in a place that is probably the most frequently burned forested area in California since fire suppression began. It's burned at least 5 times that we know of since fire suppression began. The one in 1990, it was part of the Campbell Fire, went through here, which was a 120,000 acre fire. And then in 1994, there was a 30,000 acre fire that also came through here. And this is what it left behind, because this was taken after both of those. And it's missed 2 fires now, though, because Cal Fire put them out just before they got into it. And we were hoping it would burn. And so now we're in the process of planning to try to burn it. And, so that it doesn't get away from us.
Much to Cal Fire's chagrin.
Yeah, who knows. But anyway, this is typical of what a lot of the forests look like, or the classic idea, but it isn't what they all look like. Next. From the top looking down, that's what this forest looks like. It's not continuous carpeted green like a lot of our forests are now. It's broken up. And you can see there's gaps in it, and you can see even underneath here you can see the shadows of the trees telling you it's a distance from the ground up to the crowns and stuff. And then you even have areas like this of young trees and shrubs and stuff in some of these gaps. But it's a very heterogeneous type of place, very diverse, and very diverse with the plant life and the understory as well. Next. And this is what when you walk around in it, the kind of things you see. You see here, obviously, the classic stuff that I was showing you, but then areas that look like this, even areas that are dominated by oaks and stuff that are in there, and places with lots of regen and some of the gaps, big oak tree here in an opening, and even some shrub fields that are in this. But all of this stuff is in that real diverse kind of an area. And so that when the fires do come in here, they can't sweep through it with an intense crown fire kind of a situation. The fire keeps falling out of the crowns to the ground, is basically. Next. So what we've done over the last 100 years or so is start with forests that often look like this. This is actually our Blacks Mountain Experimental Forest, when they first set up the experimental forest in the early 20th century. And And because of stopping the fires, turned it into this. Same place in 1992. And with a whole lot of difference in how fires likely to burn between a place that looks like this and a place that looks like that. Because with frequent fires, you can't get all this stuff to grow in here. You maintain low fuel loads, and that's what Mother Nature did. Next. So, stand structure, fuels, and fire behavior. This is the way we kind of think about what Mother Nature did and how we can affect fire today. And is kind of in this order. Next. First, and most important, is surface fuel. Next is ladder fuels, the stuff in the understory and intermediate sized trees. Then the crown fuels, and then also larger trees do better than little trees, all other things being equal. Now I'm going to go through each of these a little bit. Next, surface fuels that we say are the most important because where does fire start? Where does it build intensity? Where does it move to be able to go anywhere to even start going up in the trees? It's on the surface. So if you have a lot of surface fuels, then you build intensity more rapidly than if you don't. And surface fire intensity often drives primary fire effects. Which trees live, die, what happens to the soil, that kind of stuff is often driven by the surface fuels. Next. Here's a stand that was thinned and didn't bother to do anything with the surface fuels. Left them behind. This is actually a research project. And next, here's one that was thinned, and we followed it up with prescribed fire in the same project. This is both at Blacks Mountain. Next, there's what happened when the wildfire came in the area that we didn't do anything with surface fuels. It dropped to the ground. It was no longer a crown fire. It was outside. But there's enough fuel down here that it still killed over half of the trees, and it scorched them. As you can see here, all the brown scorching. Here's what happened in the other one, where we had followed up with dealing with the surface fuels. Basically, the fire dropped to the ground and didn't hurt the trees. Next. And that's how Mother Nature did it. Ladder fuels. Ladder fuels, we call them that because they provide the avenue for fire to move from the ground up into the crowns. And I show the power plant over there, that's the one burning, because actually you can remove these and generate power with them. So it's not like where surface fuels, they cost you money no matter what you do. Where these things, you might be able to recoup some of your costs if you're trying to do something with them. Next. Now this is early in the 20th century when they were first setting up Lassen Park. What they did, and they had the foresight when they were first setting up Lassen Park to actually have crews go to every section corner and put in plots, describe the vegetation, the forest that was there, and take photographs in the 4 cardinal directions. And then a colleague of mine who I do a lot of work with, he's a professor at Penn State, he was asked by Lassen National Park to come back in the 1990s and go to every one of those section corners, retake all the data, see how the forest had changed, and retake the photographs. This is the same place in 1992. And the only thing that changed here was removing fire, because it's in a national park. It was never logged, and it was never grazed, or anything like that. Just removing fire was the only change. And so it makes a big difference. Next. So basically, frequent fires of low intensity gave us forests that look like that. And next. This is what you get if you have infrequent fires, because you end up with high intensity. Next. That's the kind of fire you get going through pine needles. Next. And there's what you get with that. Because you have the avenue to go up. And that's actually a fire that was over near West. And next. Now here's an interesting picture. This is actually the boundary of our Blacks Mountain experimental forest running right through here. And we did some work there. And we also had a fire fall there. Next. This was unthinned. We hadn't done anything thinning there before, any kind of work. And all the white is ash. after the fire went. Next, that's where we had thinned it and followed the thinning with a prescribed burn 3 years before this fire came. And next, and this is where we'd actually thinned it about 15 years before the fire. And yet you can still see lots of green crowns down in there, in that area where the trees survived. And so what we did made a heck of a difference. Next. And right there was interesting. What I did was I stood right on the boundary, faced the direction the fire came from, took a picture, and then turned around and took the picture the other way. So that's what I'm going to show you. That's where the fire came from. It was actually in early September, after the longest period without rain we'd ever recorded there, driven by a north wind with 6% humidity, is the conditions that we had. What's that? Yeah, it is serious. But there, that was looking out where the fire came from. This is turning around, looking into the area where we had treated it. And the fire just immediately went down. It actually surprised us how rapidly that happened. Next. Now, crown fuels. It's interesting that independent or active crown fires in California are pretty rare. It's because of the structure of our forests. Crown fires are usually supported by the surface ladder fuel complex. The stuff that's underneath keeps it up there. That we don't have the kind of fires that typically that they have in the Rockies that get up in the crowns and just keep going in the crowns and without regard to the surface. And so basically we have what are called passive crown fires. They can be moving pretty fast, but that's the way that they're operating. Next. So in a forest like this, it's pretty much impossible to have a crown fire move through a forest like that. You can have some torching coming up from some of these trees and getting up into the higher trees, but you're not going to have a sweeping crown fire come through a forest that looks like this. Next. And then here's an example. This is where we, like I said, have done thinning with prescribed fire. And then here's that same fire. That's the result. North wind, 6% humidity, early September. And poof, it just went right to the ground and just crept through, even under those conditions. Next. Now this is a picture. This comes from right near the summit of Hatchet Mountain between Redding and Burning, where the fountain fire ended up burning through. I took this picture in 1982 because I figured it was a disaster waiting to happen because it was just so thick you could hardly even walk through it. And there's the fountain fire when it came and approaching this pass. And those trees are over 100 feet tall there. And here's what it did to the landscape. And I took this picture in as close as I could tell. It was the same place I took the first one. And I had no idea you could see Mount Shasta from there. But what I wanted to point out to you is that even in, this thing burned 45, that entire landscape you see burned in one afternoon in this fire. 45,000 acres in one afternoon. Let's see this? That little grove of trees there that survived. That's where a fellow had his house and his barn. He did his fire-safe work around his house. And it survived. And he's not the only one that worked for in this fire. It was a lot of his neighbors didn't, obviously, but he did, and there's a number of others like that as examples that survived this fire. Next. So, large trees are more resistant to fire damage than little ones. And Mother Nature created lots of big trees around here in the past because they got to live a long time with these frequent fires going through. And so basically, for any given fire intensity, a big tree is going to survive better than a little tree, regardless of the species. Next, here's kind of a characterization of it. That if you have a stand with young, old trees and then young trees under it, or just young trees, and you have, next, what we call a low-intensity fire, basically something less than 4-foot flames. When it goes through a stand like this, it'll probably kill most of the young trees, but it's not going to kill a lot of the big trees. But if all you have is young trees, then you don't have anything when you're done, because the little trees are susceptible. Next. Yeah, next. This is up near Wagon Camp, taken in 1898 by Seahart Merriam. And look at the size of the trees. I mean, these are people down here and stuff. And so you can see what I mean by the size of the trees and how far up it is to where the foliage is for them to burn. Next. Here, this is also on the south slopes of Mount Shasta, and giving you a sense of what the forest conditions look like, and here as well. That structure, and so that's what fire gave us, frequent fire gave us early on, and where forests were resilient to the fire and were able to survive through it. Next. So basically, these things are very important: surface fuels, ladder, crown, and then the big trees. Next. Now here's our cone fire. That's where we hadn't done anything. Next. That's where we had only thinned but didn't do anything with surface fuels. Next. And there's where we thinned and did prescribed fire. And so this is closest to probably what Mother Nature did, except when Mother Nature went through and had a bunch of blowdown or some beetles infestation, and you probably ended up with some of this. Next. And that's what I have for this one. This is actually a picture from on Hatchet Mountain in the early part of the 20th century, what the forest looked like. Remember what I showed you, how dense it was in '82? And there's from Hatchet Mountain, from the Wieselander work early in the 20th century. And the frequent fires contributed to that.
Would this be in the same area they have the wind turbines?
Yes.
Yeah.
Yeah, only where the wind turbines are is up above.
On the ridge?
Yeah, you can see a lot of where you see especially with the winds that go through that area there probably wasn't a lot of trees up there on the top in some of those areas anyway.
I mean, the overstory is fairly short.
Yeah, they're going to be short, and they're going to be all flagged with the wind and stuff like that, and that kind of an area. And there's a lot of shrubs up there, and that's why they're there. That would be an area where you would expect.
To tell you the truth, I've never seen them except from Rainbow Ridge, the wind turbines, 41 miles away.
Oh, really?
Yeah, you can see them from up there.
Well, they're big.
Yes.
Well, that's my talk on just kind of the how fire worked in these forests in the past, and kind of comparatively how it could work here now if we learn from the past. One of the things that's interesting is that the past, all of those frequent fires and the conditions that led to those forests we had was much cooler than today. We're much warmer now. And yet, even though it was much cooler, we had shorter fire seasons then, you still had all that fire running around in the landscape. And if basically we've been warming for about 150 years now, and fire season just in the last 30 years, here in Northern California, it's been pretty well shown, fire season has increased by 30 days, just over the last 30 years. From the time of snowmelt in the spring until you get shut off with storms and such in the fall. And so those kinds of things increase your probability of burning because you get more drying over the total course of the summer and all that kind of stuff. And so what we did is kind of interesting. We tried to shut off fire at the very time when Mother Nature would have been ramping up fire. And the forest, because of the condition they were in then, probably would have been okay to deal with it. Some of it would have gone up, obviously. It depends on where you are. But what we've done, the kind of changes we've made, is made it much less likely for the forest to be able to handle it as well. Just Bob?
Where was the cone fire?
The cone fire, it was at our Blacks Mountain Experimental Forest.
Okay. And another question, how much has the actual weather increased in temperature in the last 35 years, for instance?
What's interesting about it's actually increased considerably, the low temperature values are what have increased. High temperatures have not increased tremendously. So your afternoon temperatures haven't increased a lot. It's nighttime temperatures that have increased the most. And which is interesting, because what that is doing is that it's having it so that it's less likely to have as much freezing time as what we used to have. And that's been pretty well demonstrated. That's what I mean by lengthening of about 30 days over the course of the year, in terms of from snowmelt until you start accumulating stuff again in the fall. And so it's sufficient to cause that kind of a change. But the high temperatures, afternoon temperatures, haven't changed a lot. Yes?
So probably one of the big factors that also has had an effect on is the bark beetles, because I've heard there's not enough there's not enough hard freezes to get them, and they're really across the
Here it's
west,
not
it's
as
terrible.
big of a problem,
Right here, no,
but in the Rockies
oh,
it makes a big difference, especially the farther north you go, because
Yeah.
that's why they're able to move farther north, is because the nighttime temperatures,
aren't
the
as cold, yeah.
the coldest part of the year is not as cold as it used to be, and so it's not keeping them in check as well.
Yeah.
Such.
You had a graph, a slide showing that the predicted historical acreage burnt was like 4 million to 12 million acres in California a year.
Yeah.
This was before industrialization or colonization or whatever. I've often heard, and I've never had it confirmed, but that the Native Americans would torch areas for new shoots, to get new foliage for the
And also to improve acorn crops, and for a whole lot of
And
reasons.
clear.
Does that improve acorn crops too?
Oh, tremendously.
Does it?
Oh,
Yeah, in fact, I used to burn for that reason. We got paid by cow fishing game to do it, because the acorn crops put on fat on the deer for them going into winter range, and they survive the winters better. Yeah, Native Americans used to burn. We don't know exactly how much here and there and stuff, because nobody studied it at the time. But one of the things that we're doing a big project now, looking at all of our data up and down California, and one of the things that's interesting about it is that we see a change in fire frequency and extent of fires that seems to coincide with when Europeans settled into the area. And
A change in frequency, lower or higher?
goes lower. We end up with less fire after the Europeans come in than there was before. There was more frequent fire under the Native Americans, but less extensive fires. The fires were more limited in size, and it's probably because they were so frequent, they would run out of fuel quickly. Once the Europeans came in, the fires didn't occur as often, but when they occurred, they became larger. And that seems to be a pattern we're seeing all the way from northern Baja into southern Oregon. And it really follows nicely. And then, of course, when fire suppression comes in, then things kind of shut off. But there is that significant change that seems to happen when you get the influence of the European cultures come in.
You mentioned, go ahead.
Go ahead, Scott.
You mentioned knobcone.
Yeah.
There's a lot of it on the ridge on the north, where the ridge turns to the north.
Mm-hmm.
There's also a stand of lodgepole down by the lake, which has nothing to do with fire, and actually has to do with wind. But is lodgepole also considered like an initial tree that comes in after a fire?
Well, lodgepole will do that, but in California, lodgepole doesn't have closed cones.
And they do back east or back in Yellowstone?
In Rockies, yeah, they're a closed cone pine.
Yeah.
Here, it's the knob cone that's a closed cone.
Yes, and digger pine, yeah.
Yeah, they're partially that way. They will open over time.
Knob cone also can use cold, right, to spring the seeds?
Well, heating and cooling,
No, radical temperature change,
Yeah.
either way.
yeah.
Yeah. I'm sorry.
Yes, sir.
Carl, I was curious, as far as collecting data when you have a very high intensity burn. For example, I'm thinking of Ramshorn Peak, the Ramshorn fire when they're on the west edge of the Alps. When you have virtually no aggregations or very few residual trees left, and you're sampling and that area had burned before, and here's this compartmentalization of this scarring over old or past fire wounds that have been destroyed by the most recent fire, and you don't have the sampling of those adjacent trees, how do you make those determinations, the fire history before?
In places where it burns everything up, you don't. But what you do there is you age the trees. You can age the patterns of trees in some of those landscapes where it burned more intensely and determine when at least the last fires were. The other thing you can do is one thing we're doing all over, that would be a whole nother talk though. We've done it up here in the Cedar Basin and Mumbo and all throughout these mountains here where we core the lakes and we take sediment cores and we look at pollen and charcoal and how that accumulates over time into the lakes, and you can see when you get periods of lots of fire activity and periods without fire activity and so forth, and we can go all the way back to when the glaciers were here.
Which is when?
With that kind of stuff. Which was when? It was about between 12 and 15,000 years ago, depending upon which aspect you were on. And stuff. So Cedar Lake has a record that goes back 13,000 years. And the Cement Bluff Lake goes back 12,500, I think it is. And you can see these patterns all the way back. And you can see how the pollen changes, so you can see what climate's doing and stuff because of the changes in the species mixes over time. But like I said, that's a whole nother.
So were all those lakes ice-free by 11,000 years ago?
Yes. Yes, sir.
One of the issues, and in fact, one of the things driving these meetings is attempt or wanting to do something on Rainbow Ridge as some sort of management procedures. And I guess the central question is from your experience and the data you have, is there anything we can effectively do in the forests on Rainbow Ridge to reduce fire intensity, and maybe not necessarily frequency, but the intensity of things what we're missing. So
That's what you're interested in. Is just bringing down the nature of fire. And there is, and that was actually Eric Knapp, who is another scientist at our lab, is doing a project looking at what does restoration actually mean. And that was what I was going to talk about next. He was supposed to be here tonight to talk about that, but he ended up not being able to come, and so he gave me his slideshow to give you. And so I can do that if they're, and that's what it's aimed at is, okay, what do we do with all these data and stuff that we have? Yes?
I'm curious about the effect that the fire suppression has had on atmospheric greenhouse gas concentrations. So with the more frequent, less intense fires, how that contributed to the climate, the atmospheric greenhouse gas concentrations compared to now? Because it seems like the warming is opposite of what you would expect with fires burning more frequently, you'd imagine.
But they weren't as intense. It's actually pretty complex, but the very frequent fires that we're going through in the past left behind lots of charcoal that would become incorporated into the soil. That could sit there for 20,000 years in the soil. So that's a form of sequestration that you would get, which you are not getting now. Now what happens when a tree dies and falls over, and if somebody doesn't do something with it, then it decomposes, that releases into the atmosphere the stuff that's held in that tree. And so you don't get it going in as black carbon into the soil, for one thing. That's one change. The other thing is that this burning has gone on ever since there's been enough vegetation on the earth to burn. So in my way of looking at it, that should be just considered background. And it's the other stuff that is happening now, mostly through industrialization, that's adding to it and stuff. I mean, burning of oils and stuff like that, which would not have, in most cases, gone into the atmosphere, is going into the atmosphere. And so that's in addition to the other stuff in a tremendous way. Yes.
Essentially, wasn't the original historical fire regime pretty much a zero net carbon situation? I mean,
Oh, yeah.
you were essentially releasing about as much as was being fixed. You weren't building all this understory and these huge overstocked
And you had a lot of
stands.
grasses and herbaceous stuff in the understory that were growing, and all those fine roots that would go into the soil too. And then the trees, you know, these 400 or 500-year-old trees, that's a long time to store carbon and that kind of thing, because of the sizes of the trees that were here and such. So yeah, I'm doing a lot of those kind of projects where we are looking at carbon, and it's never simple. What do they say? The most complex problem always has a very clear, simple, and wrong answer. Yes, Brad?
A lot of the old guys and myself have been in this service since 1966. We seem to have noticed there's a lot less lightning around than there used to be. Like used to be when I was in the Forest Service as a kid, you'd see 20 lightning fires a year in an area, and now it seems like there's maybe 3 or 4 or something like that. Is there any data on the frequency of lightning fires now, the importance of lightning fires now compared to, say, 30 years ago? And is the severity of the lightning fires any more or less than it used to be 40 years ago? These are, just observations from us old guys. Is there anything to that?
I'm one of those old guys too, and
Yeah, I know.
yeah. But there does not appear to be any change in the frequency of lightning. But there is a huge change from say, earlier decades of the century to the last few decades in terms of the amount of area that lightning is that gets burned that is from lightning-caused fires. And we see this in the Sierra Nevada, and we see it here in northwestern California. Over the last 30 years, 87% of the area that is burned is from lightning-caused fires. In the Sierra Nevada, what we've seen is that lightning-caused fires before 1950 were almost inconsequential in the Sierra. I mean, it hardly made up anything. And since 1950, it predominates as the biggest cause of the most area that gets burned. And but in terms of fire severity, it's really interesting. You get more pattern, more variation in fire severity patterns in lightning-caused fires than you do in human-caused fires. Human-caused fires have a tendency to be mostly high severity. Lightning-caused fires, not necessarily. Now, why would that be? What it appears to be is that human-caused fires come 1 or 2 at a time. And they get away under very severe conditions. And so they just blast. But because there's only 1 or 2 of them, you can amass all these resources. And when conditions change to the point that you can contain them, you do it. So that you don't get much other than the high severity part in the human-caused fires. In lightning-caused fires, when they come, there's hundreds of them. They're all over the place. And it's like, okay, which ones do we do first? Well, we do the ones that are near homes and people and that kind of stuff, and we let the other stuff go. And so they're not burning under severe conditions most of the time. They only burn under severe conditions for a small portion of the time. And during the periods when they're not burning under severe conditions, we don't get severe fire effects. And so they give us a lot more variation in the severity pattern that we get. So those are, we just published a paper on that this last year, doing a really intensive look at northwestern California, and that was what we found.
Like you say, the frequency like so many storms per year hasn't changed a bit.
And what we found too is that the amount of area burned is inverse, the opposite of how many thunderstorms you have in a year. Those years that have the fewest thunderstorms get the biggest area burned. And the reason for that is those are the driest summers and those are dry storms. And when you have those years when you have lots of thunderstorms, there's moisture with them. And they're wet and they're easy to put out.
Carl?
Jim was, I think, was saying that first.
Carol, it's always interesting to me to think about historically why we decided to put out fires.
I actually had a slide to that effect and took it out.
Yeah. Talk a little bit about that. I think there's a lot, I mean, this same discussion that we're having here about whether to put fires out or let them burn, whether they're good or bad, that occurred in the 1880s and 1890s.
Yeah, I had a slide that had a photograph in it from 1912, the state forester's report to the governor. And then I also had another one, another slide that was actually from 1902, John Lieberg's stuff, and who I quoted here, talking about how important fire was for developing these forests. But he said that we needed to put fire out, and so did the state forester in 1912. And he also said some other things that are interesting I'll get to in a minute. But the reason is that if we were going to log these big trees, with all the fires that are coming through, how are those little trees going to grow up to take their place? It is essentially what the thinking was. And so it's like, oh, we can't remove these big trees and still have a forest if we don't do something with fire. Because the little trees are going to die. They're going to be burned up in the fires that come through, especially in the slash afterwards. And so that was, and that's what the state forest, the report to the governor said, and that's what John Lieberg said too in his report. And so that seems to be the main reason that we started putting fires out. And it's interesting that in that report of the state forester to the governor, he said to the governor that, he says, but the general population doesn't want to do this because they're afraid that if they keep fire out too much, that then the fires will get to the point that they can't handle them and that they need to keep burning. And he says, in fact, it's so bad that even when we can catch people in the act of putting fires out, we can't find a jury to convict. And that was in 1912. Yeah, Bob.
I am wondering if you think the lack of aggression by the U.S. Forest Service and the CDF in the initial stages of a fire are causing the huge fires and costly fires that are going on.
Well, some of the huge fires are because they have to make a decision on which ones they go after.
We've always went after all of them.
Well, see, the other thing is, though, that the fuels have caught up with us. There's more, it's like Jan van Wagendam, I don't know if you know him, he was the lead fire guy for Yosemite. And the Atkinson fire, which took off in Yosemite in, I think about 95, 96, somewhere in there, and just blasted in Yosemite. And he said that it was obvious that what had happened, because they got people there in a reasonable time compared to what they would have done in the past. He says it's just that the conditions that it's burning in, the fuels had got to the point that what were reasonable crews 20 years ago no longer work. They needed more people because of how much fuel had grown in and how much denser the area had become. And that's what I've seen in a lot of this case, is that I believe a lot of it is because the fuels have gotten ahead of our technological capabilities. They caught up to us.
Carl, just a couple comments, one time with Terry's question and comment. And your remark about crown fires being kind of uncommon in California. I've been less years than Frank over here. I started fighting fire in 1969 professionally. But when fire hits plantations, that's a crown fire.
No, that's a brush fire.
Sure is, that's a conflagration. And they just go. And that's exactly what we have on the other side of Rainbow Ridge.
Right.
That's a real concern that
Lots of plantations.
has. Because not only is that a plantation, but that's an unmaintained plantation with a lot of heavy
Yeah.
fuel.
To me, that's a chaparral fire.
That's trying
Yeah,
to take
it
over those plantations there.
Yeah.
So it's a pretty spooky deal. And then the other thought I had in relation to lightning fires, you know, me being a student of fire ecology for more than a few years, 40-some years, I think lightning is just plain unpredictable. Like 2008, you said, is the big year that we had, the biggest year ever recorded. And the
For area
lightning activity level was rated as 2 on June 21st. I think it was 21st when it broke out.
Yeah, they blew that.
Yeah, well,
I mean,
and yet, you know, there's the fuel moisture in the wrong place, or, you know, the right places, I guess, the wrong places to burn. But 2 weeks before, there was lots of fuel moisture. And then we got that heat drive.
that was actually the driest spring on record.
The what?
2008 was the driest spring on record for Northern California.
But we did get some rain. We did
Yeah,
have quite a
but
bit
it
of
didn't-
moisture, you know, 2 weeks before.
Yeah, but it didn't affect, it goes away.
Yeah.
Unless
Yeah,
it
when they
sits
left,
there.
When that heat came.
Yeah.
And
And
then it did burn.
so it's not like it went deep into the fuels. It was something that was very short-lived. And where basically, if you look at the charts, 2008 was the driest year, the driest spring that we've ever recorded in Northern California. And it set us up for those early fires.
Yeah, it did.
But I don't know why we were surprised. That's what gets me. Why were we surprised?
Because it's a new generation. You know,
Because we were expecting it. It's
Tell
like,
you that.
hey, we got the driest spring on record. We know when the thunderstorms come, we're going to have fires. And everybody seemed to, oh wow, what happened? And I don't know. Yes, Julie.
Just to add a couple things, Dale, on that too, is the fire modeling that we can do. And I don't know if anybody's done that yet on Rainbow Ridge, should be a really good thing to do, but the plantations, we model them as type 4 brush, which is your,
Not as trees.
no, it's like chaparral fire, because it's
Yeah.
just, that's a
That's
lot
exactly
different
what
than
this
an
is,
actual
for sure.
stand, you know, it's like, it's not.
Yeah.
And then the other thing also on the 2008 fires, there was actually, we had a bit of a drawdown. We had crews elsewhere in different places, and so when they triaged, or we call it that, when you prioritize some of those ones farther out in the wilderness areas, they just put as a lower priority and they more attacked the ones closer, just like Carl was saying, toward the urban interface. And they had no idea some of those would move the way they did and went down towards Big Bar and the towns as much as they did. So there's only so much they could do with so many resources, and that was part of the problem too, so. Yeah.
And that's real relevant too, Julie, because that certainly was the case in, say, 77,
Oh, yeah.
Okay.
81,
87,
99.
yeah. Everybody was
You know,
in
fire burning
75.
south, where do they go? They go where the populations are. They go where the high-value resources are.
Another reason to condition your forests, because there won't be anybody here.
Yeah, well, we stripped out possibly.
How old do you have, well, I guess maybe Bob would tell us, how old is the plantation on the backside of Rainbow Ridge? When did it burn? It must have burned before 62
Well, actually, the plantation was put in the 80s, is when it was put in.
When?
80s.
80s?
That's when I was
When
working
was the
here.
last fire?
Wasn't that 1986?
It was about
And
that,
it came
yeah.
up to heavy brush, a lot of it.
Because I was working on the district at the time that the plantation was put in.
When was the last fire in there?
It was in the big fire that went through there was in the 40s.
Your 40s? Was that the last fire to go through there?
The last big one, yeah. It depends on when they get the money to do the work. That's right.
I tend to suspect that Disraeli was correct when he said that there are lies, damn lies, and statistics. But given the immensity of the forested area that we have, what about the economics of this fuel control? How does it pencil out?
It depends on where you are. If you're on pretty flat country.
Well, if it's my house, I think it works out fine, yeah.
If you're on the
It's
country
all about
between here and the
access.
coast, it doesn't. And so
Yeah.
it just depends on where you are and as to whether it pencils out. And the other thing is it depends on how close you are to a facility that can use the material and those kinds of things. It's like after the Megram fire over on the west side of the Shasta Trinity, and it blew through under a north wind kind of a thing and a blowdown that had happened in the winter and stuff a few years before. And I was there with the guys that were representing the biomass industry and stuff, and I says, okay, tell me how much of this you guys could actually utilize if it was opened up to you. And they basically said none. They said it's too far from any of our facilities. It would cost us too much to get it there. It would have to be subsidized. So it depends on where you're going. And but if you're close to a facility and you're in relatively flat ground, then it does pencil out.
Yeah.
But I should get onto this though.
Yeah.
And because what it is, this is kind of a neat study. And restoring resiliency in variable density thinning on the Stanislaus Tuolumne experimental forest. Stanislaus Tuolumne experimental forest is in the central Sierra Nevada. It's just north of Yosemite. And it's in mixed conifer. It was originally dominated by sugar pine with ponderosa pine and white fir and incense cedar as the main species and black oak. So it's not that different than forests around here in that regard. And so this is what we've been doing next. Is actually this is what was said about it, and these are pictures from it early in the 20th century. And Shao and Kotok, early foresters with the experiment station, and went on to actually Shao became the regional forester for a while. And this is what they said in 1924, was that the virgin forest is uneven aged, or at best even aged by small groups, and is patchy and broken, and hence it's fairly immune from extensive, devastating crown fires. And they had seen fires in it a lot. And it says, fire creates a patchy, scattered distribution of reproduction. And so you can see there's a lot of variety in the patterns there. I mean, you got some dense areas that might torch if a fire comes through, but then it's going to run into this or that. And so fires moving through this forest have a lot of things in the way. But what happened here next is I found some maps. And it might look kind of weird. But Duncan Dunning was an early research forester, and he put in plots on the experimental forest. These are 20-acre plots. They are 10-acre, actually, where they map every tree, and it's given a number, and so forth. And at first I wondered, wow, where are these? And I asked around the office, and nobody knew where these plots were, except on the experimental forest somewhere. And so I turned it over to Eric Knapp when he came to work for us. I said, hey, look at these maps. These are really cool. If you can figure out where this is, you've pretty much got your career working on this project. And so anyway, next, what they did was, see, every tree is numbered. All of these points is a different tree out there on these 10-acre plots. These are the down logs. These are the understory shrubs. Those things, those were all mapped in the understory. They even put transects through like this that recorded and got cover of all of the understory herbaceous grassy vegetation. So they know what everything was that was living on these things way back when. They even mapped where the rock outcrops were and stuff. I mean, nobody has this kind of data from that time period from anywhere else. And next, the trees still have their tags. And we can find, he finally found the boundaries, and he did this by going to the National Archives and finding where the data sheets were kept from all of this. And then he was able to go back and find all this stuff. And they even put in photo points that showed you what it looked like at the time. This was in the 1920s. And then they logged them in different intensities and stuff. And so he's been going back through remapping everything over the last few years to show how these forests have changed since that period. Next. Here's kind of how they sit. There was a heavy cut, a light economic thin, and then a U.S. Forest Service thin, which was even lighter than the light economic thin. And that's what they called them back then. The heavy cut was take absolutely everything that you could make a dime off of. And then this one was not being so harsh, and that one was even less so. What's interesting is that they all look the same today. That's the thing that's, they're all equally as dense today, which is interesting. And that's that shows you where it sits in California. Next. So, in 1929, basically, there was an average of 116 trees per acre, greater than 4 inches in diameter. In 2008, that's up to 276 trees per acre. This is the basal area. You know what basal area is? That's the amount of area that the base of the tree sits on the acre. And you total that all up, and that shows you how much area is occupied by trees. And so it's increased considerably, and the proportion, though, in pine has gone from 37% down to 21% over that time period. So it kind of shows you how things have changed. Next. And if you look at the trees and you draw circles based on the size of the tree, this is 1929. And so you see lots of big green, that's sugar pine. And then this yellowish stuff is the ponderosa pine. And the brown is incense cedar, and the black is white fir. And then look at what has happened up to 2008. And you can see a whole lot more incense cedar and white fir is basically what you see, and not very much ponderosa pine. Next. So, if you put this into a model and in a computer, it kind of gives you an idea on 1 acre of how the trees would be arrayed. And so that's what Eric did here. And he shows you what it looked like in 1929 and next. And there from the side, looking at it, what it would look like. And you'd have a few big trees, some little trees, but you can see how they're spatially arrayed. They're not everything is not everywhere. Here's what it looks like in 2008. It's changed considerably. And then here's what it looks like this way. And so this is going to burn a whole lot differently in a fire than that is. Next. That would be a goal. What you wanted to do was restore a condition. You would want to push this in that direction, is where you would want to go in terms of restoration. Next. And I found this picture, which was kind of neat, that is very similar to that when you look at it. And this is actually taken just north of Lassen Park, is where by Leaslander early in the 20th century. And so it kind of gives you another view of what that might look like in terms of patterning and such. Next. But this is what we do today. We don't have that kind of heterogeneity in the forest. We go in and we pretty much just do the same thing throughout. We even it out, and makes it easier to work that way, but you don't have the patterning, the spatial patterning. You have reduced the ladder fuels, you have raised height to crown base, and changed things in that way, so you have reduced fire hazard here. But it's not restoration in terms of the variety of conditions that were there before and how that would have affected wildlife habitat and understory vegetation and other things besides just the trees. Next. And so what variable density thinning does is restore structure and pattern in a way similar to what fire would historically have produced. It reduces the risk of high severity fire moving across a landscape, and but it helps to maintain or enhance habitat for a variety of species, because you don't do the same thing everywhere. And there's that tree right here. It was a really fast-growing sugar pony, because it was, when they did the logging in 1929, it was just under 11 inches in diameter. And you can see what it did since then. It's pretty amazing. And it got released. Next. So basically what Eric has done is mapped everything, the old trees, these are from the old ones, and looking at basal area. And it's like an average doesn't cut it. And what he's showed, here's a place where you don't have any trees in this particular little compartment. This one you have 159 square feet to the acre. This one over here, with all these big trees all packed in there, you have 481. Down here's just little trees scattered about, so you have 45. And so what does an average tell you? It doesn't tell you anything. And so what they've been doing is figuring out how to recreate this kind of diversity. And they actually did it last summer with, they went out and marked everything and had the loggers come in and recreate this. Next. And so this is kind of how they arrayed it in the landscape, different compartments and different, they have, what they're going to do is do prescribed fire on half of these units and leave prescribed fire out of half. But they have high variability areas, low variability, which are more similar to what we typically have been doing the last few decades. And then the untreated areas. So we can compare, and wildlife people are involved and vegetation people are involved to see how everything responds to this over time. Next. And so basically the main elements of this are to create small openings, size, frequency based on the historical maps, and visualize the forest as a series of approximately quarter-acre groups, and vary the basal area density and species mix within these quarter-acre areas. And next. So here's some examples. The trees with an arrow next to them are the ones that are going to be kept, and the other trees are going to go. So here's a medium density, medium size. This one over here is a low density, large size, so just the one tree in there is going to be kept in that particular group. Next. And then here, came out being a high density, large size. And so all of those trees are right there are going to be kept and stuff in order to try to match the kind of patterning that used to be there. Next. And so here's what it looked like after logging. Here's where we have a low density one with the pine and a gap around it. Here we have some high density areas and such. Next. And then also there's where that group is that I showed you before, and how that turned out. This is immediately post-harvest, as you can tell. Next. And then here's a group of large trees, only a little lower density and such. And so getting all of this kind of variation in there throughout these areas. Next.
Is that a west aspect?
Most of this it goes from a kind of a northerly to westerly is the way the forest runs. And then next. And so within groups, we'll basically also try to retain the best trees regardless of the crown spacing. In other words, we don't say automatically don't let crowns touch or something to that effect. It depends on what kind of grouping that particular area came up to be. Next. The other thing is that black oak is important, especially for wildlife species of many kinds. And so there are places that come out being, okay, we're going to release the oaks in here as well, and back the conifers off of them. And because we know that a lot of these big old oaks, they didn't grow up in a dense forest, they grew up in an open forest. And then we need to also maintain some of these regeneration, younger trees as well. So all of this is what we're doing. And next. And the concept of restoring more variability in resilient forest conditions has really broad support from a diverse group of stakeholders. It's really interesting, the people that have bought into this there. You have people from the timber industry are supporting it, as well as the Sierra Club and the Wilderness Society. That they've all visited it, they all seem to like what they see, and we weren't sure what the Sierra Club was going to say when they showed up. We had their representatives from their main office in San Francisco come out there, and they actually thought it looked pretty good. And we were actually surprised at that, and so that was good. Next. And so basically, we also diverted from in the Sierra Nevada, they have a 30-inch diameter cap on what they can cut under their current forest plans. Anything over 30 inches you don't cut no matter what. And in this particular study, they let us divert from that. If it turned out that we thought that tree didn't belong in that particular place, and usually that was the white fir that had grown in since the original logging. So they actually took out some pretty big trees in there. But what is removed should be a function of a current stand relative to the desired resilient and condition that you want, and such. And so basically, in this case, they looked at resilience as being the presence of large fire-resistant trees plus this heterogeneous or diverse stand structure. And so that's how the information is being used. He's analyzing a lot of the data now, and there's more detailed papers are going to be coming out. And so that's one paper that describes all this was published this spring in a general technical report. And so if anybody's interested, I mean, we have it. And I was hoping Eric could be here, and he would love to come and actually get out on the ground with some of you folks and talk about these concepts on the ground. Next. Oh yeah, acknowledgements. The Stanislaus National Forest has really helped with this. There are people, it was interesting. At first it was kind of like, they were kind of resistant. Not all of them, like Maria here, she was all for it from the beginning. And she's the district ranger there now. She was just really for this and very supportive. But a lot of the people, say like the timber marking crews and people like that, they were very resistant because it's kind of like, oh, it's hard. This is hard to think about. And it's not like you give me 5 rules and I can go out and do it. And but after Eric spent a lot of time with them and with the different environmental groups and people on the ground explaining why we're doing this and what it's going to teach us, and pretty much everybody bought into it and really went for it. And then the Sierra Resource Management Incorporated is the logging contractor who did the work in the area. And it's interesting, the fellow, when he came to the SAF had actually a field tour here before they did the work. And Eric was explaining to them what they were going to do to the Society of American Foresters. And the owner of this company was there to see it, and he wanted it bad enough that he bid it so that he got it, and because he wanted to be able to do this work, and he was very big. So that's why he's up there. They're up there as acknowledgements too. Next.
That was on the Meanwood Ranger District?
No, it's on the summit.
Oh.
It's right near Pinecrest.
Yeah, very, very high recreation use area.
Oh yeah, in fact we get joggers and bikers, bicyclists and people through there all the time. I mean, yeah, it's, there's a picture of what he used to look like in McLeod Flats.
Don't look like that anymore.
Oh, you haven't asked a question.
One thought is, as we're here thinking about Rainbow Ridge, and there's several large landowners along with several smaller subdivision areas, and the thought for a lot of folks has been, how do we think like a landscape? How do we work around our houses if we have larger lands? how do we collaborate, not just, you know, that the process of working together person to person, but how do we look at this ridge in that way that you just did? And is there a size that is a manageable size or not a manageable size when it comes to looking at that variable, what was the term you used? Variable mosaic or variable.
That's good. Diverse.
Right, then so, you know, if there's a 40-acre landowner next to a 10-acre landowner with a thin strip and maybe another thin strip, you know, is there a certain way you want to approach looking at a ridge line
Well,
when you have
remember,
such a diverse land ownership?
yeah, that's a very good question. But one thing to remember is fire doesn't see property lines.
Right.
And
That's
you know, number one.
How do you erase those?
Yeah.
Conceptually, but not recognize them practically.
Yeah. Well, part of that comes from, I think, something that Julie suggested, is doing some modeling. And because when you model it, then you can see, you get a better idea of what you can expect fire to do in that environment, regardless of who owns the land.
So a rainbow ridge model.
Yeah, that kind of thing, I think, helps to do. And, but the other thing to remember is that based on what we saw at Black's Mountain and what I saw in the Fountain Fire and stuff, even treating small areas, if you treat them sufficiently, can make a big difference for that place, and even if it doesn't affect things around you the way you would like it to affect the landscape. And so that's something to think about too. Is, so it depends. If you get a lot of cooperation from a lot of people, you probably don't need to treat the landscape as intensively, because you can treat more of it and give it more variety. If you don't get a lot of cooperation from a lot of people and you just have a few here and there, then those particular places probably need to treat their areas more intensively in order to keep from being affected by what's happening
Interesting.
from the neighbors.
Thanks.
Well, one comment and a question, that if you're using a matrix patch size of about 1/4 acre, those fit into almost any parcel size. I mean,
Yeah.
5 acre, 10 acre, 1/4 acre pieces, if that's how you're doing your mosaic, you could stick to a property line but still work within that parcel, so that's pretty usable. Well, one question is, how did they treat the slash from that operation? Did it get removed? Did it just get masticated? Or?
Well, see, that's what that's the next phase of the study is. Half of the units are going to be burned, and the other half we're going to leave them as they are. That's the way it's going.
And that gets tricky too, because if you're on private lands and things, obviously you're in a Forest Service situation there, so you have prescribed fire managers and people that can apply it and
Right.
with the science that we do with prescribed fire. So if you're on Rainbow Ridge, you can't just go start burning your property. I mean, you gotta be careful. I mean, I'm saying you can't, but you gotta be watching.
You can do it,
Part of
but
the process of bringing people along is to convince them that private landowners have to
Do fuel reduction.
They have to do fuel reduction,
Yeah.
but if you want a fire resilient habitat, you have to burn your property somehow, or rake the whole 10 acres
You
and
gotta deal
and
with the
dispose of
surface
it.
fuels.
Sure, you have to deal with it somehow, so, and I mean, I've experienced a small underburn on my property that was not by design, but I saw the results, and I'm committed now. 60 acres are going to slowly get burned, one little piece at a time.
you know, I grew up on a farm up on Hatchet Mountain, like I said, and we actually did a lot of burning. And our neighbor was the one that started us doing burning and stuff. And he had a story that he used to tell that was kind of neat. That he had lived on the place next to where I grew up since 1906 was when he moved there. And he said that they would take the cattle in the spring and drive them up into the meadows on Hatchet Mountain and leave them there all summer, and then they go up in the fall to get them. Well, we've all heard that kind of story before. But what he said that they did when they came down with the cows was they would take a long rope and they would soak the end of it in kerosene and light it on fire and drag it behind the horses as they came down there.
Wow.
That's racehorses, huh?
No, he says the fires just crept around and they burn here, they burn there, and everybody just wandered their way back down the mountain. And they did that every year. And what's interesting about it is that by the time the mountain fire came, there were almost no meadows left on the edge of the mountain. It had turned into Manzanita brush fields. And that's where and so they couldn't graze cattle.
Well, on the Stanislaus there, in terms of the understory and whatnot, did they just do a commercial timber operation, or did they do biomass shipping as well to get some of the submerged stuff, or is that all?
Oh, for this project?
Yeah, for that project.
Yeah,
was
they
that
did the
all part of the
biomass.
berms?
They did biomass stuff as well, too.
So all the, okay.
Yeah, definitely. Now, one thing, we just published some papers on, you brought up the word mastication, and that's where you go through and you mash the stuff up somehow, shred it, mash it up, something, and if you can't burn it, and kind of spread it around and hope that works. And what we have found is that, yeah, it does bring down the tendency of the fire to be able to go up into the crowns. So it gets rid of your ladder fuels and that kind of stuff. But what it does is that you haven't removed any fuel. You just spread it around and you made it more continuous. And so if the area does burn, you're likely to actually girdle the trees or do root damage to the trees from the heat of the fire working its way through the masticated fuels. Unless crews can, but it does make it easier for crews if they get there to actually put it out and stuff. So there are advantages and disadvantages when doing it. Jim?
Carl, one thing I always think about with these, you know, we talk about making a fire resilient forest or a fire resistant forest or resistant around our house, that it's difficult because things change rather rapidly. We see that in areas we've treated that stuff grows back. And I kind of think that even like your comment about mastication, we can change how fire behaves by modifying fuels. Is another kind of overall strategy.
Right.
And part of what you're doing with the quarter acre, which is about the size of this room or so, 50 feet by 50 feet or so, you know, you're changing the structure of things.
Yeah.
And even if you don't remove all the fuels, which in some cases isn't necessarily a good thing either, soil fertility and wildlife and other reasons, there's a lot more to it than just fire issues in managing the forest. But anytime we can modify fuels, we'll modify fire behavior. And like Julie was saying, the modeling, we can look at, well, what kind of fire do we want to kind of be resilient to? And that might be another way of looking at this, is that, you know, we've got fire engines parked pretty strategically close by, and if we do have small fires and the fuels aren't really severe, we can get to them pretty quickly.
Right.
We don't have to make a landscape that is completely, you know, kind of fireproof. Right. And that may be another kind of practical way of looking at this too. But we just don't want it where if we are in a situation where we don't get to the fire in a half hour, it gets up to the tops and starts heading up the hill, and pretty soon it becomes a pretty big fire pretty quick. Or the winds are pushing it pretty severely.
The way I look at it is you need enough variation in the structure and pattern to interrupt the flow of fire as it moves across the area. And there's even some computer models that have looked at, okay, if you have catastrophic fire conditions, what does it take to interrupt the flow? And what do they call it? Splats. Strategically placed area treatments. So he calls them splats. But and there's certain percentages that you can put into landscapes, and you'll stop the big conflagrations. It won't stop the other stuff in between. But then if what you want is to more make your smaller properties, say like 10 acres, 40 acres, more resilient, then thinking along the lines of the kinds of stuff that Eric is doing, I think, would go a achieving that.
I wasn't here for the first meeting because I was out of town. But part of the whole Rainbow Ridge area, when I was in the fuels officer position on the district, we were working pretty closely with SPI to develop a starting point with a quote fuel break. We more like fuel management zone is almost a better way to put it than fuel break, but working along the whole ridge top, since you have that road system that goes along the ridge top, to work with that as a starting point, and then from that, working to sort of what Carl's saying, sort of break, if you can break it up a little bit, that's sort of a great way to start, and that did get going pretty well. I'm not sure if...
SPI logged in there 3 or 4 years ago, and then
Yeah, and they did
came
the...
back in 2 years ago and did the
Yeah.
ridge top.
They did, and the
Took the
Forest
slash
Service
out.
was, just, you know, we
And the Forest Service did a
it.
slash removal.
Yeah, we did, we
in
attached,
Section 13.
right, so we,
About 3 years ago.
I actually wrote some of the plans and
And
they
they're about to
finally
be
got going
The
on
next
it.
section too this year.
Okay, but what needs to happen is it needs to continue on
That's what I'm saying.
the other
They
direction.
did 13, now they're gonna do section 12, which is. the
Okay,
more-
good. Well,
and
see, that's a
section-
starting, that's a
Yeah.
great way to start. It doesn't mean, I'm not saying, of course, there's a lot more land on the aspects that need to be treated, but at least you're having a starting point, an anchor point, so you can burn from it or do things from it. So that's a really good start.
Well, now that SPI's logged most of, they own most of section 19, and they've logged it pretty good. It's really reduced the fuel levels up there a lot.
Did they treat the surface?
Disagree with that being.
Did they treat the surface?
I
Yeah,
totally
on
boundary with that
2
section.
chains on the top, they did.
It's not like that.
What's that?
There's no fuel reduction in that, on that section. My property borders that section, and the fuels on the ground now are extremely high.
I'm talking about the ridge top. Section 19 is pretty much denuded as far as anything less than 10 inches BPH.
So you're saying the slash fuels, the activity
The
slash?
slash is really.
From the log?
Yeah, on the
That-
SPI ground, it's really problematic.
Yeah, they
Yeah,
left,
I agree.
they left a lot of slash, no doubt, but on top of the ridge, they took it out and
Yeah,
actually
and that
had,
needs to be, definitely needs to be attended. Somebody, that's a great place to start looking at what that slash needs to be treated. Because just like Carl said, it all starts at the surface fuels, it's really important.
In answer to the, or maybe to comment on the lady's question,